The goal of section 1.2 is to use the length and the midpoint of a segment, and also to construct midpoints and congruent segments. The distance between points H and G on this ruler is exactly 0.5 centimeters. Between J and G is 2 centimeters. Between G and J is the exact same segment, just the endpoints are reversed in order, so that one's also going to be 2 centimeters. If we compare those two answers, we discover that the distance from J to G is the same as from G to J. To form a class definition of distance, we're going to go back to some Algebra 1 skills. We're going to take the absolute value of the difference of the coordinates. Distance cannot be negative. The same is true for absolute value. That's why it's a great tool here. On this line, there's only one dimension, so the coordinates are not x comma y. It's just here's d at 0, here's c at 2, and here's e at negative 3.5. So what does it mean to find the absolute value of the difference of the coordinates? If we took b minus e, for example, b being negative 4 and e being negative 3.5, since we're subtracting a negative, that turns into addition, and we get an answer of negative 0.5. Does it make sense to say the distance between these two is negative 0.5? Not really. We take the absolute value and it comes out as 0.5. We could do the same, take 0 minus a negative 4, and this time it just comes out as 4. We can also just try to count over using the number line. Both will give us the same answer of 4. When a segment crosses 0, that's when we have to really be aware that we're adding together two distances. This distance is 2, and this distance is 3.5. If we add those together, we get our answer 5.5. Or if we subtract the 2, we take the absolute value and we get a positive 5.5 as well. The segment addition postulate just being something that is true, says that if you add together segments AB and BC, you get the full segment AC. So two parts of a segment, when you add them up, they equal the whole. Using this idea, you can figure out that one part, y, plus another part, 5, is equal to the whole, 7. If you solve, y is equal to 2, and that's what jk is, 2. Similar scenario here, you have 8 plus z is equal to 14. That's AB plus BC is equal to the entire thing. So z is equal to 6. They want to know what BC is. That's going to be 6. You just substitute it right in. Sometimes you have to draw the diagram. And we'll just stick A in the middle of C and T. It might not be perfectly to scale. They tell us this part is 9. The entire thing is 14. What's the missing part, AT? So 9 plus what is 14 is really what we're saying. If we call this x, 9 plus something is equal to 14. That's going to be 5. Notation-wise, we can say jk is 2, and bc is 2, and at is 5. Notice we don't have the line above to indicate these are segments, because we're saying the distance, or the length, is equal to this value. Pay close attention that when you solve for the variable, like n here, that's not always going to be your final answer. They want to know what the distance sv is, so that's going to be 2n minus 1. So if you plug that in, 21 times 2, 42, minus 1, 41. Similar in E, we find that A is 15, so we can plug that in here to figure out what xy is. And xy is going to be equal to 21, 15 plus 6. A couple of vocabulary terms. If two segments have the same length, we can call the segments congruent. And you would write that like this. Segment AB, with a line above it to indicate the segment, is congruent to segment CD. This symbol here means congruent. It's an equal sign with a little squiggly on top. That's the formal name. If we're just talking that the lengths are equal, you would say length AB is equal to length CD. And you don't have that little line above. Next up, a midpoint divides a segment into two congruent parts. So in this case, AB is equal to BC. You could say that. You could also say that segment AB is congruent to segment BC. Then there's a couple different types of segment bisectors. The definition is a line, ray, or segment that intersects a segment at its midpoint. So we have segment AB for all three of these pictures, and there's a midpoint, exactly halfway between A and B. Whether we cross that with a line, or with a ray, or with another segment, they are all considered segment bisectors. They cut it into two parts, and specifically two equal parts. We can use this to find some unknown lengths. For example, segment PQ is going to be congruent to segment NP. We know that because P is the midpoint. So its lengths are equal. And we can write that 3x is equal to 2x plus 4. And if we subtract 2x from both sides, we get that x is equal to 4. If we plug that back in here, we can find out the length of NP. And NP is equal to 12. And we already found that x is 4. If we wanted to find NQ, you could separately plug in 4 for here as well. 2 times 4 plus 4, which is also 12. But if we know one of these lengths, we know the other. P is the midpoint. It divides the whole thing in two. So if NP is 12, then NQ is going to be 24. So let's do a quick check. Can we tell if E is a midpoint here? Well, since we have DE and EF are adding up to the whole thing, if that was true, we could take 1/2 of the total length, which is 6x, and that's what we'd see on both sides. 3x on the left, 3x on the right. Do we see 3x here? No, it's not a midpoint. Some of these you have to draw your own diagrams. If this section is 5x and this one is 3x plus 4, can we find all three of them, knowing that it's the midpoint? First thing we do is we set the two equal to each other. We subtract 3x from both sides, we divide by 2, x is equal to 2. If I plug that back in here, 3 times 2 is 6 plus 4, this distance is 10. If I plug in 2 over here, 5 times 2 is 10. So you could say AB is equal to 10, BC is equal to 10, and AC is equal to 20.